Hi, this is my video for or my project for Calculus 1, and I wanted this video slash project to be a 101 on what calculus is. So my goal is for maybe if a new calculus student were to watch this video, it helps them kind of understand the rough idea of what calculus is and what it's about. Um, to start off with, calculus is pretty new. It's it's pretty recent compared to other areas of mathematics. It was founded in around the 1600s by, it's argued it was either Newton or a guy named Leibniz. But compared to other parts of math like geometry, we got that from way back then, ancient Greek back then. So this is pretty new stuff compared to other fields of math. And calculus, its purpose is mainly about change. It's about predicting change. How that looks mathematically would be graph-wise. It could be described as you have a graph, right? And instead of, the straight graphs that we've all been used to in algebra and all that, we get a weird, wonky wave graph. And calculus has basically two tools to deal with this graph. One is to find the slope, or you can call it steepness, of a point. And its second tool is to find the area of a graph, or a section of graph. So for this section, you would find the area of this graph. Those are the two main tools you'll be dealing with in this class. But how does this work? You may be probably asking. I know I asked myself how the hell that's supposed to work. For the slope part, we call that a derivative. And you can think of it as slope, and as you know, or I hope you know, slope is your rate of change. It's your delta y over delta x, or your difference in y over your difference in x. Well, the way we used to get it was we would have a line on a graph, and we would pick 2 points, plug in those values, solve. You would have probably done it with y2 minus y1 over x2 minus x1. But you can't really do that when your graph isn't so nice and straight. It decides that it kind of wants to mess with you by doing this wavy nonsense. Well, how would you find the slope of this? We can't use the slope formula that we've gotten so accustomed to. Well, imagine that you were using Desmos or some sort of graphing website, and let's say you wanted to find the slope of this point. You would zoom in. You would zoom in on this point so much that it just kind of looks like this. And you would have your point here. And you would pick another point, let's say here, and you would draw a line. Now, what you just did is you made an approximation of a slope. It's close, but it's not quite the slope. Well, that's not good. This is mathematics. You want to be precise. Well, how do you get more precise? Well, it's pretty simple. Just put your second imaginary point a bit closer to the point you want to find. Draw a line. And you will keep doing this over and over and over. You get a point here, draw a line, point here, draw a line. And when you get so close, eventually it's gonna start to resemble a tangent line. And some of you might not remember what a tangent line is. I probably didn't, but it's nothing too scary. It sounds scary, but it's nothing that big. A tangent line is just when you have a graph and you just want to pick a point where a straight line meets it. That is the definition of tangent line. You don't need to worry about it too much. It's not that scary. So, from this concept, what we have established is that the closer your the closer your 2 points are that you pick, the closer your approximation is. And you're gonna approach a certain number. So, for example, you do y2 minus y1 over x2 over x1 on a point you picked, and let's say arbitrarily you just get a number like 0.97. You put these points closer and your answer is going to be something like 0.98. Put it even closer and it's going to be 0.99. Put it even closer, it's going to be 0.999, and so forth. The closer you get, the more it's going to go on. It's going to go 0.99999, 0.99999, on and on and on, until you're approaching a number. And it's a sort of plateau. You can't get past this number. And that is what we pick as our slope, our derivative. Our number is approaching this. And while that is our derivative, I suppose that could also serve as an explanation to limits. But I'm not going to delve into limits that much, because otherwise I feel like I won't be able to get into everything in calculus. And I'll probably make a separate video. Yeah, probably my next project video, I'll make it just solely on derivatives. Then I'll head into limits. So that is our basic view on derivatives. And if you remember what I said earlier, our second tool we use in calculus is integrals. And again, like all of calculus, you deal with a not so pretty graph. Now, instead of just finding the slope or the steepness of a certain point, we are finding the area of a section of a graph. For example, let's say we want to find the area of the graph in this section. We want all that. Well, how do we go about this? I mean, we're used to formulas for area. I mean, rectangles, length times width, triangles, 1/2, base times height, all blah, 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 blah. But most of the time, you're dealing with something symmetrical or something straight. It's got angles, you can see it, you can apply it. But with these curved graphs, well, that's not so easy, is it? Well, let's say we were to take the section of the graph that we want to find the area of. So it's going to look like something like that. Let's just imagine cutting it out so we can inspect it a bit more. Let's say we try to fit a bunch of strips. Oh, these rectangular strips, almost as if you're cutting this graph. When you're imagining it, imagine it just a slightly more neater than me. I have the shaky hands of an 80-year-old man, so sorry about that. Now that we have fitted these rectangular strips into the graph, let's say we found the area of all these rectangles and we added them all up. Then we would have, again, a rough approximation of our integral, our area of this graph. But it's a really rough approximation. Why? Because look at all this gap, all this space that we have not accounted for. It's terrible. This is very bad estimate. No one would use it. But imagine, similar to derivatives, we decided to take this idea to the extreme and cut this graph up into just so many strips, so many rectangular strips, that it's just a bunch of lines. such a lot of strips. So many and so fine that you practically can't see these empty spaces we saw earlier when we did our previous approximation. We can't see that no more. That's how fine we got. Well, then our area is, again, like our derivative, going to approach a certain number. Since it's an area, I'll use a bigger number. Let's say that our first approximation, our integral, our area, was something like 17.2. And we'll chop these strips up finer and finer until we eventually get to something as absurd as this. And our answers will go from 17.2 to like 17.4 to 18.3 to 18.7 to 18.9. And then, like our derivatives earlier, it's going to start to plateau. It'll be 18.99, 18.999. Our integral, our approximation of our integral, is going to approach a certain number and not get past. And when that happens, we get to say that our area, our integral, is the number that is being approached. That is what integrals are. So, slightly more complicated topic, I suppose. Now, right off the bat, you can probably already see two similarities between derivatives and integrals. And if you don't, let me tell you. Derivatives and integrals both A, deal with approximations, and B, they both deal with changing variables. What I mean by that is, well, if you look at a graph that is super curvy, all that, there's no, it's not like it has a slope, a constant slope, like a straight line would. It's not going to rise to, run 1, rise 2, run 1, rise 2, run 1. Curved graphs like these fluctuate. Their datas are variables. They change, which is why calculus is used to compute change, to predict change in several fields. There's so many fields that use not even complex calculus. Just the very concept of calculus is used worldwide. It's a very important topic, a very painful topic to learn, at least for me personally, but it's very, very important. That is undeniable. So, where would you see this in a day-to-day scenario? We know that in Calculus 1, you're given two tools, derivatives and integrals. Derivatives measure rates of change, the slopes of curves. Integrals measure area, the accumulation under a curve. But how does that relate to, how does that help us IRL? I mean, for me personally, it was hard to understand, like, okay, you have a curved line, you can find the line, like, basically a tangent line, which serves as a slope, okay, you have a curve of an area, you know what is this helpful for? Well, the simplest example I can give you that you would realistically see in a day-to-day basis is when you drive. I mean, I'm assuming you're a college student. You probably commute at least. You have to take a taxi, you have to take a train. You're going from point A to point B. Well, calculus can be used to determine whatever you're in, velocity and acceleration. Okay. Let's say you're in a car and you're going to point A to point B. Maybe you're going from your home to a Krispy Kreme. I mean, right now I can go for a donut, yeah. Or a Starbucks, or maybe from college to your home. Either way, you're going down let's say a straight line, just for convenience sake and time's sake. And you know that the position of the car is given by the function s of t equals 5t squared plus 2t plus 1. And what this basically means is, if you were to take your time, be it hours, seconds, something, let's say you're 60 minutes in on a drive, you would plug in your t, and it would spit out, you've went 17 miles, you went 18 miles. It gives you a distance. That's what this function serves as. S of t is our position, and t is our time. Now, with this information, how do we use calculus to find out our car's velocity and our car's acceleration? Well, we find the velocity function. And what is velocity really? Velocity in layman's term is the rate of change of a position with respect to time. And, well, what do we go over that's rate of change? Oh, right. Derivatives. Well, how do we use derivatives? Well, you'll get into this more, but you would derive this equation, and I can't explain how you derive in this video. Maybe a different video. Yeah, the next project video, probably going to be derivatives. But you would derive this function s of t equals 5t squared plus 2t plus 1. And that would give us v over t 10t plus 2. Again, not going into the details of how you derive, because this is meant to be a 101. It's supposed to be give you a general idea of what you're going to get into. Now, if you were to derive this formula, you get 10t plus 2. Don't focus on how you got it. Just know that. And this function, this new function, is going to represent our car's velocity at any given time, any given t. So if you want to know the car's speed at a specific moment, just plug in t. Well, let's say we want to know the velocity of our car 2 seconds in. Well, that would just be v2 equals 10 times 2 plus 2. And let's say that's 22 meters. Yay! That's your velocity. Well, how do we find our acceleration instead? Well, acceleration is the rate of change of velocity, not time this time. But it's still rate of change. So we can get the derivative of the function we derived. We would call this our second derivative. We would derive 10t plus 2, which would give us just 10. This means that our car has a constant acceleration of 10 meters per second squared. Again, this is a simple explanation. I mean, obviously, IRL, you're not going to be going at a constant speed, and you're not going to most likely go at a straight line, and you're most definitely not going to keep going ahead without any stop signs. But this just serves as an application of calculus. You'll get into this after you understand derivatives and integrals. You're gonna start to apply these in practice problems like these, but on a much more complex scale, and we call those applications of calculus.
It's 3 p.m.
And this was one example, but I just want to throw a bunch more examples just to really hammer in the point that calculus is really used everywhere. We can see it used in astronomy. You could see it in business. We can see it in marketing. We can see it in economics, meteorology. You can use it to find the payment structures. You can use it to get modeling systems, calculate rates of change, all of that, price elasticity. Calculus is essentially everywhere. And Calculus 1 is going to help you just recognize seeing it more.